Another important topic in Chapter 5.4, or at least in what some books do for 5.4, is called the Net Change Theorem. It starts by looking at the Fundamental Theorem of Calculus 2, Part 2, so go ahead and write that out real quick. Hopefully you remember it. It wouldn't be bad to look it up. All right, so let's say it's the integral a to b f of t dt equals, and what does that equal to? Big F of b minus big F of a. And let's remember that little f here is the rate of change of big F, because big F is an antiderivative of little f. So little f is the rate of change of big F, or you could say little f equals big F prime. So you could write this with a big F prime there instead of little f. So this, we could say, is the accumulated change of f, big F, little f is the rate of change, and we're accumulating all those little changes. And over here, this is the final minus initial, which is the net change in f. So f of b is the final value, and then we're subtracting the initial value, and that's the net change in f, in big F. So sometimes we use that, or we can rearrange it and get a little bit more insight. All we need to do is add f of a to both sides and flip the order of the equation. So it's not really any fancy algebra. F of b equals f of a plus integral a to b f of t dt. So this is saying the final amount is equal to the initial amount plus the net change, or the accumulated change, so you take your initial amount, you add how much change happened between the start and the stop, and that gives you your final amount. Let's do a quick example. It does have a little bit of a twist in it, so let's see what happens there. Let's say you have a tank with 3,000 gallons of water. And water is flowing out at a rate that changes with time. So we're going to say that's f of t equals 200 minus 4t gallons per minute, where t is in minutes. How much will be in the tank after 10 minutes? So the first thing I do is draw a picture. We'll draw the world's best picture of a tank. And there's some kind of water level inside, and we're losing water out that way. We could draw the function we were given. So we know f starts at 200 and decays at some rate. What do we think will happen for big F? We know it starts at 3,000, and we're losing water, so we think overall the amount in the tank is dropping. Is it dropping linearly? Is it dropping in a concave down fashion? Is it dropping in a concave up fashion? We're pretty sure it's dropping, but we don't know exactly what the shape is. So I'm guessing we can use the net change theorem here. We could say the amount in the tank at time 10 is the amount in the tank at time 0 plus the integral from start time to stop time, so that'd be 0 to 10. And we'll write the 200 minus 4t, that's the rate at which we're losing water, times dt. And it's a pretty straightforward integration problem, right? Do you see any potential problems here? Take a minute to look around. Well, we think the amount should be decreasing, but here we're adding something that's usually positive. So we need to realize the twist here is that this net change is usually positive when we're adding stuff, but the function we're given here is actually taking stuff away. So that's the water is flowing out. So I need to throw a negative in here to indicate that this is flowing out. So we're going to highlight this flowing out and say that's why I have the negative there. So go ahead and do the integral and pause and do the integral and then come back. So the initial amount is 3,000. And then what do we do with this integral? I would put the minus out here. The integral of 200 is 200t. The integral of 4t is 4 times 1/2 t squared from 0 to 10. And then that's 3,000 plus negative 200 times 10 minus 4 times 1/2 times 10 squared minus, plug in the 0 here, 200 times 0, 4 times 1/2 times 0. Now here I got, I was okay, I would have been okay if I didn't have the parentheses because this was all 0 anyway, but if I hadn't had a total of 0 in there, then I would have really needed those parentheses to make sure that this minus got distributed properly to that minus. So if we do all that, we get minus 2,000 minus 200 minus 0 minus 0. So we get 3,000 plus negative 1,800, which ends up being 1,200 gallons. At time 10. So that's a fairly straightforward use of the net change theorem, except with that little minus sign because we were talking about outflow rate rather than addition rate. This is okay. It's kind of a, I mean, we are thinking about the level of water dropping, but it's just giving us a single answer. It might be more interesting to ask, what does the shape of the curve look like as the water leaves the tank? So we could basically redo all of this and say not just at time 10, but we could ask what's happening, or what's the water level at time t. I'm going to use a capital T here because I have a lowercase t in there that should get substituted out. But we could say it's 3,000 plus negative, and just anywhere you see a 10, replace it with a capital T. So 200 capital T minus 4 times 1/2 capital T squared, and then there was the 0 minus 0, so we'll just leave that out. So we could go type this into Desmos and see what shape we get, and then also take the derivative and make sure that we're getting our rate of change function. So let's go do that. All right, here I've typed in our rate of change function. We're losing water at a rate of 200 minus 4t gallons per minute. And this is the net change function we got using that capital T. Really, once we've already done the substitution, we could have used a lowercase t or even an x, but an x would feel a little weird because it's not, it doesn't sound like it's related to time. So here's our water outflow rate. It's just that linear function. And here's the rate of the water level in the tank as time goes on. And we said it should end up being 1200, and so looks like it's right. We said we were curious about the shape here. The shape seems to be slightly concave up. It does look like a parabola. It has a minus on the t-squared, but then another minus. So overall, it would be kind of an upward parabola, and we're just seeing kind of the first part of it, that initial downslope. So it's decreasing but concave up. Could we have predicted that based on the behavior of the flow function? We'd be saying, well, this flow function is getting closer to 0, so the initial outflow is fairly rapid, or more rapid than toward the end. So this should be dropping more rapidly at the beginning than at the end, which is what being concave up is doing here. We also said let's check capital F, and now if I put a t here, Desmos would get confused, so I'm going to use capital F of x, capital F prime of x. Do I get the same curve as I put in for my rate function? No, those are not the same, but they are similar. The issue is, remember, this was an outflow function rather than an inflow, so there's probably just a difference by sign, and that does seem to cure the problem. You know, one thing we forgot to do is an upper bound and lower bound and guess and everything. Let's zoom back in on our outflow function. Where did it go? Okay, that's going to take a while. There we go. So we wanted basically the integral of this from 0 to 10. We could have put a lower bound line at y equals whatever that value is, 160 it looks like. We'll put that in red because we usually do lower bounds in red. We could have put an upper bound line at y equals 200, that maximum value, and we've been doing those in blue. And then we could have put a guess line halfway between those. So 160 plus 200 divided by 2, which is 180. And we've been doing our guess lines in purple. There we go. So one thing we could say here is, gee, it looks like, yeah, the flow was 200 to begin with. It got down to 160 near the end. That's kind of averaging out to be 180 gallons per minute. So if I said 180 gallons per minute times 10 minutes, that would be an overall outflow of 1800, which turned out to be exactly what we saw. And then we're not surprised. Our guess looks like it would be exactly right, because we are including some area in the guess here that shouldn't be included, and that exactly matches the area that we're missing for this upper triangle. So because this is a nice linear function, our guess turned out to be exactly right. But I also like this idea of saying, sure, the flow rate is changing, but you know, it's not changing all that much, and it's just kind of averaging about 180. So that's a good beneficial way to think as well.